In the early 1990s, while studying cancer prevention, biochemist Dr. Judith Campisi was investigating how cells respond to stress. She noticed something unexpected. When cells were damaged by toxins, radiation, or simply time, many didn't die, they just stopped dividing. Campisi called this state cellular senescence, a built-in safety mechanism that prevents damaged cells from becoming cancerous. But there was a catch. Instead of disappearing, these cells lingered. They began secreting inflammatory molecules that harmed nearby tissue, a phenomenon she later defined as the senescence-associated secretory phenotype, or SASP.
The first major discovery she made was the identification of a marker that allows us to identify senescent cells from non-senescent cells. And so once you can actually measure and identify something, you can then study its mechanism and also look for interventions that can actually revert this process. So what is cellular senescence? It is a normal cellular process by which a cell that detects an abnormality, for example, in its replication. Let's say that a cell carries a new mutation that makes it proliferate faster than a normal cell. There's an inborn mechanism that will force these cells to slow down. Obviously, if it starts replicating or dividing too fast, it has the risk of becoming a cancer. And so the process of cellular senescence recognizes this abnormality and puts the cell in a resting state.
When our cells get damaged or too old, they sometimes stop dividing instead of dying, kind of like a machine that shuts down but never turns off. These senescent or zombie cells stick around and release chemicals that irritate nearby cells, slowly causing our tissues to age and break down over time. The idea was revolutionary. Aging itself could be traced to the buildup of senescent cells. Over time, these zombie cells act like tiny biological saboteurs, degrading tissue, weakening organs, and amplifying inflammation throughout the body.
These cells, you can imagine them accumulating, and we can detect them in people as young as 25, 30-year-old, meaning that that protective mechanism of senescence works throughout life. Now, there's a secondary aspect of senescence, which is the fact that these cells start churning out, secreting a number of markers that tell the immune system that the cell is now senescent. It's called the SASP. And another discovery from Judith Campisi. The role of the SASP is to tell the immune system, and here's an abnormal cell, you need to come and destroy it. And that process works out throughout life. The problem is the clearance mechanism, we think, is not 100% foolproof, which means that these cells tend to accumulate as we age. As they accumulate, they keep churning out these inflammatory markers, and the current model on which we are working now is that they contribute to what's called the chronic inflammation associated with aging. Inflammation is a normal process that allows you to heal, but when it becomes chronic, as we see in aging, it can actually become by itself a source of disease. And there's growing evidence that this chronic inflammation from senescent cells plays a key role in these diseases. So now this has led to the idea that we should try to get rid of these senescent cells, and we have drugs now that we call senolytics. And when we apply these drugs in animal models, we can suppress the chronic inflammation associated with aging, increase lifespan, and actually prevent the development of all these chronic diseases of aging.
Dr. Campisi's discovery transformed our understanding of aging. It revealed that the process is not fixed, it's malleable, shaped by how our cells repair, renew, and communicate over time. Cellular senescence is now recognized as one of the hallmarks of aging, alongside mitochondrial decline, DNA damage, and stem cell exhaustion. By studying how to slow or reverse it, scientists are learning not only how to extend life, but how to preserve vitality, cognition, and purpose in the years we already have.